In the last video, I set up half of a producer-consumer application using the thread-safe array blocking queue as a shared resource. I've got the project open, the parallel streams and more project, and I'll be adding code to the visitors list class. First, I'll create a master list of visitors. This will represent the Park system's currently registered visitors. Our visitors center only wants to give out discounts to new visitors. I'll make this private, static and final as well. This time though, I'm going to use a copy on write array list and not an array blocking queue. This class is also thread safe, but it's not a fixed size and it never blocks. I'll call this master list. I'll populate this list with a static initializer block. Because this is final, it's the only place other than the declaration statement itself to assign a value. Again, this is a good opportunity to review the static initializer. It also lets me demonstrate one way you can collect a stream of elements into this concurrent class. A static initializer block starts with the word static. I'll assign master list to the results of a stream pipeline. This should look familiar. I'm generating an infinite stream of persons. I don't want duplicate persons, so I'll use distinct. I'll limit it to 2,500 distinct persons. Remember, each customer is unique by the combination of name and age. This should severely limit the number of new visitors we encounter. Finally, I can use the collect terminal operation that takes a supplier first, so that's a method reference for a new copy on write array list. Because I already specified the type in this collection in the declaration, I don't have to specify it here because it can be inferred. The next argument is the accumulator, so a method reference just to add an element to this array list. The last is a combiner, so add all goes there. That should hopefully limit the number of new visitors. Next, I'll set up the consumer runnable. I'll insert that just after the producer runnable. I'll call it consumer. I'll get the thread name. I'll print that and the text, polling queue, then output the queue size. The poll method returns the visitor at the head of the queue. If the visitor is not null, I'll print which thread is processing which visitor. I'll check if this visitor is in the master list. A record includes an equals method which checks equality for each field. This means a visitor will match if their first and last name and their age are all equal to a person in the master list. If they aren't in the master list, I'll add them. I'll also print they're new and should get a coupon. Finally, I'll print the new visitor's queue size again after this process. Since I want several consumer threads running, I'll create a thread pool. I also want this to be scheduled. I'll call the variable consumer pool. Then I'll get a new scheduled thread pool with 3 threads at the start. Since I wanted to schedule 3 tasks, I'll wrap this in a for loop. In this case, I'll use the schedule at fixed rate method. I'll pass the consumer task. I'll have the first task start after 6 seconds have elapsed, then I'll have them scheduled at every 3 seconds thereafter. Now, I need to shut the consumer executor down at some point. I'll add this code after the producer executor shut down. I'll copy the while loop and the shutdown statements for that executor and paste a copy at the end of this method. I'll change the producer executor to the consumer pool in the try block. I'll also change that time from 20 seconds in the await termination to 3 seconds. Lastly, I'll change producer executor to consumer pool in that last statement, shutting down the consumer pool. I'm also going to change the timeout in the await termination call for the producer executor from 20 to 10. Before I run this, I'll delete the drain queue text file. Since I'll have consumer threads running, I don't expect this code to execute, but I'll remove that file just in case. I'll change the print statements in the producer runnable code so the output will be easier to understand. First, I'll change the adding statement to queuing. I'll also just comment out the line that prints the entire queue in the if statement. Okay, so looking at this code, I should get 5 visitors queued up before any consumer threads get started. While the 6th visitor is waiting to be queued, in the offer method, for that 5 seconds, the consumer threads will start polling the queue, and this 6th visitor should be successfully added to the queue. This means the code won't be writing to the draining queue text file. 3 consumer threads will work on the queue at fixed intervals, starting up every 3 seconds after an initial delay of 6 seconds. This will give the single threaded producer the chance to add 3 more visitors to the queue. Okay, so let's run this and see what we get. You can see the visitors queuing up every second. It pauses at the 6th visitor. Remember, the call to the offer method, has a 5-second timeout. So it'll wait up to 5 seconds to succeed. Meanwhile, you can see the consumer threads polling the queue. Each finds a full queue. Each will get a visitor at the head of the queue. Notice that each got a different visitor. This means the array blocking queue is doing its job, managing the head of the queue efficiently in a multi-threaded environment. After processing, the queue size is 3. That's because the producer was able to add that 6th visitor while these threads were processing their element. So we'll see this continue. I should also see statements that 1 or 2 visitors added to the master list and getting a coupon. One other thing I want you to notice is that the poll method doesn't block if the queue is empty. It just returns a null value. I'll come back to this in a minute. First though, I'll run this again. Again, I want you to see that 1 or 2 visitors are added out of a total of 9 or 10 queued. Adding visitors to the master list is an infrequent occurrence, which is the reason I chose the copy on write array list. The name copy on write is important. Whenever this list is modified by adding, updating, or removing elements, a new copy of the underlying array is created. The modification is performed on the new copy, allowing concurrent read operations to use the original unmodified array. This ensures that reader threads aren't blocked by writers. Since changes are made to a separate copy of the array, there aren't any synchronization issues between the reading and writing threads. This is ordinarily too costly, but may be more efficient than alternatives when traversal operations vastly outnumber mutations. Although this example, with 9 or 10 reads, didn't vastly outnumber changes, meaning the 1 or 2 inserts, you can imagine that a master list could contain hundreds of thousands of visitors, or new visitors might be a small drop in the bucket. In this code, I used a poll method to get the visitor from the queue. The array blocking queue has several different methods to get an element from the queue. Most of these will get the element at the head of the queue, or the first in. If the queue is empty, a method will return null or block as described on this slide. I've included the pick method here because it will return an element from the queue, but it doesn't actually remove it from the queue. This method could be used to check the queue before attempting a blocking method. I showed you an example of the poll method with no arguments. This method simply returns a null if the queue is empty, as I demonstrated in my code. The overloaded version of this method takes timeout information and will block for that duration. In addition to the poll method, there's also the remove method. Calling this method with no arguments will return an element if there's one on the queue, or it will block indefinitely until an element is added to the queue. This method doesn't throw an interrupted exception, so you can call it without a try-catch block. The second version of the remove method is significantly different. It lets you define which element you want to remove from the queue and doesn't return the element, instead it returns a Boolean value. Finally, there's the take method, which, like the no args remove method, blocks if the queue is empty. This one, though, throws an interrupted exception. So that's a lot of options. I want to get back to my code and try a couple of these other methods. First, I'll change my poll method to include a timeout. This will make my code more efficient, forcing a thread to hang out and wait, rather than disposing of a thread and creating a new one when there's no work. Getting back to the consumer runnable code, I'll add the timeout arguments to the poll method. I'll make this 5 seconds, so a thread will wait up to 5 seconds for a queued element to be added. This code won't compile because this method throws the checked exception, interrupted exception. I'll use IntelliJ to surround it with a try-catch. I'll change the rate the producer adds a visitor from 1 second to say 3 seconds, so the queue will be empty more often. I'll also change the fixed rate so that the consumer threads run more often every second after the first delay of 6 seconds. I'll run the code this way. 3 visitors are added by the time our 3 consumer threads are kicked off, and those 3 threads can do their work. But then you can see the 3 threads polling again and getting an empty queue, a queue with size 0. Then the producer adds a 4th visitor who's immediately processed by one of the waiting 3 threads. At this point, 10 seconds have passed and the application ends. So this was a bit harder to see, but I hope you get the idea. You might have a good reason for waiting a little bit to wait for elements to be added to the queue instead of trying, then immediately failing. Next, I'll try this using the take method. I'll replace the poll method with its 2 arguments with just the take method. This causes an IntelliJ warning on the if statement, which I'm going to ignore because visitor may not always be null, so I'm not sure why it's giving me that warning. I'll run this code. This code runs as it did before until the second round of consumer threads encounter an empty queue. Now, my application just hangs and never shuts down, so I'll stop it manually. There might be very valid reasons for blocking indefinitely and having these threads waiting here. In this video, I used this consumer producer example to introduce you to 2 more thread-safe classes. The array blocking queue gives you a lot of different options to control and manage the shared data being processed. The copy on write array list is useful when the shared data is mostly going to be accessed for reading. An expensive copy of the array list is made if adds or updates are made to the list, so make sure you know how your shared list will be accessed before making a decision to use this type. The alternative to the copy on write array list is the concurrent link queue, which I discussed on a previous slide. In the next video, I want to review some of the other threading problems. We've seen one example of a deadlock. I'll review another example, then compare that to the live lock and starvation problems, so I'll see you in that video.